Welcome, ladies and gentlemen. Let's go ahead and generate the fourth order Taylor polynomial that represents the given function. So here we have f of x equals x times e to the x. What do we need to construct the Taylor polynomial? Well, we need derivatives, right? We're going to start with the value of the function at x equals 0, but then find f prime of 0, f double prime of 0, f triple prime of 0, up until the order of the polynomial. So we need 4 derivatives here. So we'll go ahead and jump right in. We need f of 0, the value of the function. We need f prime of 0. We need f double prime of 0, and so on, up until the order of the polynomial, so we need 4 derivatives here. Notice that the prime notation gives way to that little number up there telling you what number derivative, right, we're going to after you get third derivative. All right, so let's go ahead and see if we can evaluate the function at x equals 0. Well, that's easy. 0 times e to the 0 is 0. In order to get f prime of 0, I'm going to have to differentiate my function. It looks like product rule, right? So the derivative of a product of two functions is the derivative of the first times the second plus the first, plus the first times the derivative of the second. And hopefully as you're differentiating these, right, you notice a pattern here to make your life a little bit easier. But for now, evaluate at x equals 0, we get 1. You guys getting 1? Cool. F double prime is the derivative of f prime, and evaluate at x equals 0. So let's see, e to the x differentiates to e to the x. And then when I differentiate this product, didn't we already do that with our first derivative? So what am I going to get? I'm going to get e to the x plus x e to the x, evaluated at x equals 0. And now it looks like I get 1 plus 0 is 2. Yes? Awesome. We'll do one more, and then we're going to go ahead and jump to the pattern. As I differentiate f double prime rather, to get f triple prime, I get e to the x plus e to the x plus, there's my product again, x e to the x differentiates to e to the x plus x e to the x, evaluated at x equals 0. And Tyler, you notice a nice pattern here. Each time if you were to factor out that e to the x, you'd get the order of the prime, right, plus x. And so this would be e to the x times 2 plus x. This would be e to the x times 3 plus x. And I bet this would be e to the x times quantity 4 plus x. So that's pretty sweet. Evaluated at x equals 0, we get 3. All right. And then we can do the same thing here. Are you guys comfortable jumping right to f? Fourth derivative, evaluated at x equals 0 is 4. Can we do it? All right. Great. So that is the derivatives of my function, evaluated at x equals 0, through the order of my polynomial. That is through the fourth derivative. But that's only part of the coefficient on my power terms, right? I still need to divide by n factorial, where n is the degree of my derivative. So let's go ahead and see if we can expand this just a touch. I know then that my fourth order Taylor polynomial, we can write with a little subscript there, p sub 4 of x, just to represent our fourth order polynomial, is given by f of 0, which is 0, right, plus f prime at 0 was 1, x to the first divided by 1 factorial is just x, plus my second degree term has coefficient 2 over 2 factorial, x to the second, plus my third degree term has the value of the derivative, third derivative at x equals 0, over 3 factorial times x to the third, and one more, move it. Just want to get one more fit in here, plus my fourth derivative, 4 over 4 factorial x to the fourth. Okay, so I'll do one rewrite to make it easier to work with and make it look a little bit prettier. So p sub 4 of x is my fourth order Taylor polynomial, is given by x plus 2x squared over 2. Is that just, what's that? X squared? Is that just x squared? plus 3x cubed over x, sorry, 3x cubed over 3 factorial is just x cubed over 2. Anything x cubed over 2. And my final term, I get x to the 4th over 3 factorial, which would be x to the 4th over 6. All right, moment of truth. Go ahead and raise your hand if you had the 4th order Taylor polynomial correct. That's where you need to be as a result of our activity thus far. Nice job, you guys. Okay, so what can we do? Well, we can then generalize this not to be the 4th order polynomial, which again is just a partial sum, a truncation, right, of the exact function representation as a series. The Taylor series would then span out to an infinite number of terms, right, an infinite number of terms. Could we generalize the pattern seen thus far? Well, let's see. We had, I want to try and do this, and I'm going to try and do this, and I'm going to try and do this. Oh, goodness gracious. So if that's my 4th order Taylor polynomial, I'll call it p sub 4 of x. Could I generalize the pattern and write a representation, a series representation, right, for the function that is an infinite series? That would be the Taylor series. Well, certainly. If we look at our terms, right, it looks as though my degree of every term goes up by 1, right? And my denominators, how would I get our denominators there? Well, let's see if we can't represent that. So it looks like sum from n equals, and we can decide if we want to do 0, and if we want to do 0 to infinity. Do we have to do one more? We better be sure here. What would the next one be? So the next one would be 5 x to the 5th, bless you, over 5 factorial. Is that right? So the next one would be, so 5x to the 5th over 5 factorial. And that would reduce to 5x to the 5th over 4 factorial. So I think it's useful to keep this as 3 factorial, 2 factorial, and then, all right. So do you guys want to start with 0 as my index start value or 1? Okay, so we'll start with 0. We know then that my first term is x to the n plus 1, right? So this is x to the n plus 1. If my first term is x to the first, when I plug in 0, then I need to have n plus 1 in order to make that work. And then I know that 0, 1, 2, 3, so that's fine. But I need to divide by, looks like n factorial. Would that work? So then my 0, 1, 2, so when n is 2, I get x to the 3rd over 2 factorial. When n is 3, I get x to the 4th over 3 factorial. When x is 4, I get x to the 5th over n factorial. So it looks like this is the series representation called the Taylor series. And if it's centered at x equals 0, then it's called the Maclaurin series. Danny?
And n equals 0, aren't we dividing by 0?
That's a great question. So when n equals 0, we're dividing by 0 factorial. But 0 factorial is defined to be 1. Okay, so 0 factorial is defined to be 1. So if we did 0 math PRB 4, it's defined to be 1 back with our combinatorics and probability. And so we're okay. But always something to consider. Good. Could we have written that with an n start value of 1? Certainly. Then our index would just be starting with 1, so x to the n, and then over n minus 1 factorial. We won't get around the 0 factorial problem. By doing that, we just change our expression. But 0 factorial is 1, so we're okay. Great question. Others? All right, so let's go ahead and see where we are for the day. Well, we need to take care of our OTL check. I'll go ahead and pause the recording to do that. Okay, ladies and gentlemen, thank you for your help with that. I appreciate it. Today we're going to continue with our Taylor series introductory activity. Right? We're also going to generate some new functions from old functions. And so after we complete our stamp and we get down our familiar functions, Maclaurin series table, copy down into our notes, we're going to come back together and use those to generate some new functions using what we know about power series representations already. So once again, most of you have gotten stamps already from the 2H first two, the 2B second two, 4, and we're right around the 5E 6B. So I'm going to go ahead and pause the recording. I'd ask you to scoot into your groups and continue on after everybody's received their 6B and done their copying. Then we'll come back together and have some more whole group discussion. Okay. At the end, we do need to put the test and testing information for my AB class later. Excellent. Questions about what the next part of class is going to look like? Cool. Let's go ahead and scoot into our groups and get going then. Okay, and so as a result of our introduction to Taylor series activity, we should now be able to generalize, right, the nth order Taylor polynomial approximation of a function centered at x equals 0. So this is on your day 4 notes, and I included one slide for the series on today's, but there's a difference between the polynomial representation versus the series representation. And so if you'd like to grab your day 4 notes, this is what we didn't get to last time. You're welcome to copy this into your day 4 notes. Or if you don't have your day 4 notes with you, you could certainly add it to your day 5 notes. Just make sure you're making a distinction between the polynomial, the Taylor polynomial, versus the Taylor series. How come? Well, the Taylor polynomial is an approximation. It's a partial sum, right, that represents the function. The series is the infinite, right? The infinite sum that represents the function. If the series converges, then the Taylor series, right, equals the function over the interval of convergence. The Taylor polynomial will just be an approximation of the function. So the key is that you evaluate the nth derivative, right, at x equals 0, divided by n factorial, times x to the nth power. Right? That's the generalized term. If we then, it turns out that we don't have to center our Taylor polynomial at x equals 0. We could center it at any x value, right, at x equals 2, or at x equals -3/2. In which case, we'll follow the same exact process. It's just that we'll evaluate our derivatives not at x equals 0, but at x equals a. So we need the function value at x equals a, the first derivative, second derivative, third derivative, and so on, evaluate at x equals a. And then my power term, instead of being x to the n, becomes quantity x minus a to the n, just using transformations. So all we'll do is we'll shift it over our a units to center it at x equals a. Exactly the same thing, right? See, we're just evaluating the nth derivative now at x equals a, divided by n factorial, and then times quantity x minus a to the n. These two forms are equivalent. I mean, the first is, right, is a special case of the generalized second form. When x equals 0, right, then we wouldn't write that quantity x minus 0 to the n. But it's certainly equivalent. So while the Taylor polynomial is an approximation of our function, what's really cool then is the Taylor series representation of a function centered at x equals a. And so this is now back on your day 5 notes. Right, did I get you a new one on day 5? Great. So how can we generalize that? Well, Taylor series then is an infinite sum. So we can go ahead and write that with our summation notation. N equals 0 to infinity. In general, then will be the nth order derivative evaluated at x equals a over n factorial, then times x minus a to the n. If the Taylor series is centered at x equals 0, then we have what we call the Maclaurin series. Again, that's just a special case of the Taylor series when it's centered at x equals 0. And that's how you probably generated your cosine, right? Taylor series for the n, you center it at x equals 0. That's called the Maclaurin series. In the course of the past 3 class periods, we've generated Taylor series now, before we knew they were called Taylor series for several functions. And what we now know as Maclaurin series when they're centered at x equals 0 for some common functions, starting with our basic geometric, right, series 1 over 1 minus x. We also did it for inverse tangent, e to the x. Now sine of x and cosine of x gets added to the list. We did do an ln of 1 plus x. But what we're going to do now is use those power series representations of some common functions to build some new functions. Okay, but first let's make sure we're good now with our Taylor series, whether we're not centered at x equals 0. So let's find the Taylor series centered at x equals 1 for the function. On your OTL, you're going to have to do some Taylor series that are not centered at x equals 0. What do we need? Well, we need the same thing. And so we're going to go ahead and start taking derivatives until we can generalize the pattern, because again, this is not asking for the Taylor polynomial like Bellwork. This is asking for the series. So we need to be able to generalize the nth term and write the infinite sum. So what do we need? Well, we need f of not 0 this time, but f of 1. We need f prime of 1. We need f double prime of 1. We need f triple prime of 1, and so on. We're hoping that, right, we don't have to continue doing this until the 20th term to recognize a pattern. We're hoping that we can recognize a pattern so that we can stop it, get the generalized nth term, and then write the Taylor series. So here we go. F of 1, evaluate my original 1 over 1 is just 1. F prime of 1, we need our first derivative. So differentiating our reciprocal function 1 over x gives us negative 1 over x squared. Evaluated at x equals 1, and I get negative 1. Is that what you guys are getting? Let's do f double prime. F double prime would be the derivative of negative 1x to the negative 1 would be positive 1x to the negative 2. So I'm getting 1 over, this should be x squared. Sorry. So that would be negative 2 times negative 1 is positive 2x to the negative 3. Evaluate at x equals 1 gives me positive 2. Are you using positive 2? Did I work that out finally? So now I'm going to leave it here as this direct power function. It's going to be way easier to do derivatives now. This looks like negative 6x to the negative 4. Evaluate at x equals 1 is negative 6. Well, looks like I'm going to have to do a little bit more. Or am I? My fourth derivative, evaluate x equals 1, I get positive 24. Now that number should look familiar. X to the negative 5, evaluated at 1, is positive 24. If you recognize our values of my derivatives at x equals 1, well, excluding the sign, but 1, 2, 6, 24, what kind of numbers are those? Factorials. And so I think we have a generalized pattern. Do I have to keep going ad nauseum here, right, to get the Taylor series? No, let's go ahead and try to write the generalized nth term. And so it looks like my nth term, as I start with my series representation, 1 plus, a negative 1 already, so I'm going to have to change that. So far I've got 1 minus 1 over 1 factorial times quantity, and it's not going to be x to the first, it's going to be x minus a. In this case, x minus 1. Does everybody see that? We're centering this at x equals 1, not at x equals 0. So instead of having x to the first, we're going to have quantity x minus 1 close quantity to the first, plus 2 over 2 factorial quantity x minus 1 to the second. Alright, getting too big. Let's keep it going. Next up, minus 6 over 3 factorial. Quantity x minus 1 to the third, one more, plus 24 over fourth order would be 4 factorial, or n factorial, times quantity x minus 1 to the fourth. Do we have enough to generalize it? I think we do. What's special about 24 and 4 factorial? They're equivalent. They're just 1. 6 over 3 factorial, 1. 2 over 2 factorial, 1. And so I'm ready to generalize it. This is just, wow. 1 minus 1x minus 1 plus x minus 1 squared minus x minus 1 cubed plus x minus 1 to the fourth dot plus, and here we go, it looks like my generalized nth term, yes that's right, the generalized nth term we'll use for our Taylor series representation in just a minute, is given by alternating sign. You guys have seen how to do alternating sign, right? We've got our negative 1 quantity to the, and what's it going to have to be? It looks like it's going to have to be to the n. If we started with 0, then that would make negative when we have the odd 1, and positive when we have the even exponent 2, a negative when we have the odd exponent 3, so that works. Quantity, and now we'll have x minus 1 to the, and what will we have? 0, 1, 2, 3, so just n, straight up. Is that it? Do we need any n factorial on the bottom? No, we've taken care of that with our value of the derivative, right? And then divided by that n factorial. And so, our Taylor series representation then is the sum from 0 to infinity of my generalized nth term, negative 1 to the n times quantity x minus 1 to the n. That's pretty sweet. So not only can we center at x equals 0, we can center at any x value. It's just with transformations. Emily.
So if it says, like, it's centered at 1, you can then, when you're doing the summation, center it at 0? Or, like, start it at 0?
Oh, for this index?
Yeah.
That's not connected to the value which it's centered. This is where we start our evaluation to expand it and generate these terms. And so this 0 has nothing to do with where it's centered. This 0 has to do with our start value when we go to expand that summation notation. So this is what I plug in here to generate the first term, the second term, the third term. So that's not connected with this. This is where I'm centering it, and that's where I evaluate my derivatives. So these things will always match. If I center it at x equals negative 3, then there will be negative 3 here, and it will be x plus 3 here. Everybody see that? Cool. Let's go ahead and check the reasonableness of my answer by drafting the original function and the fifth partial sum together in the same window, and we have a good pattern here. So I don't think this will take long. Let's go ahead and go to our y equals menu, and we'll clear out that business. In our original function, I'll put in y1. Let's do 1 over x. And our second function, let's go ahead and put the fifth partial sum from our Taylor series expansion. So for us, we already recognize the pattern. We see 1 minus quantity x minus 1, which certainly would reduce, but to keep it straight for me. So 1 minus x minus 1 plus, bless you, x minus 1 squared minus quantity x minus 1 cubed plus x minus 1 to the fourth, and one more, minus quantity x minus 1 to the fifth. How many mistakes did I make, Riley? You're pretty much in charge of that. Okay, so what window do we want? we want to check around 1 minus x, and we are centering on x equals 1. So let's go ahead and try maybe negative 2 to 4, right? We could try negative 2 to 4 maybe. And we could try negative 2 to 2. Maybe. If I don't like it, I'll just change it. All right, let's see how we do it. There comes our reciprocal function, 1 over x, and here comes our fifth partial sum somewhere. Oh my gosh, look at that. So that does a really good job, right, in this window here near x equals 1, but what happens when we get over by x equals 2? Well, it diverges from that, right, from that series. What would you expect to happen if we added, right, more terms to our partial sum? Well, we'd expect it to do a better and better job. However, this interval of convergence, right, is it going to be infinite? Well, there's no hope for it being infinite. Look over here at my reciprocal function, 1 over x. It's centered at x equals 1, but there's no way we're going to be able to handle that asymptote with our polynomial partial sum Taylor polynomial expansion. Kobe.
If we centered it at -1, would it latch on to that other part?
Absolutely. So we could certainly go back and center it. How come? Because now we'd be evaluating our function at x equals -1, and the first derivative at x equals -1, and the second derivative at x equals -1. So we'd be building our function right here and taking the exact behavior of my original, right, in order to construct my Taylor polynomial. Awesome. All right, cool. It's a little bit bigger. Awesome. What questions do you guys have about our Taylor polynomial centered not at x equals 0? All right, let's build a new function then. So, building new functions from old. Let's use our table of our elementary functions. Several of you completed the table, several of you didn't. That's okay. We'll be able to check in our text. We're going to go ahead and construct some new series and then make a connection back to our original Bellwork problem. So let's use known Maclaurin series. Remember, that's just a special name for a Taylor series centered at x equals 0 to construct the Maclaurin series for the new function. Before we start cranking out derivatives, I want you to know that you don't have to for your book problems as well, right? Because these series are basically polynomial expansions. We can follow our same rules with order of operations, right? We can add them, we can subtract them, we can multiply them, and we can see how our series representation changes as a result of those operations. So this looks like it's based on some Maclaurin series we already know. We already know the Maclaurin series for sine of x, don't we? And so what if we just started out with our sine of x representation? What? Well, isn't sine of x, right? Isn't sine of x given by, and that was my, let's see, x minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus x to the 7th over 7 factorial. Is that right? So our sine function representation, that's only the several terms here. I'm going to make this smaller. And what's our generalized form for that? So what would our sine of x generalized form be? Well, it looks like it's -1 to the, how'd you guys do it? Did you guys do n plus 1? To the n? And it starts at 0? Is that going to work? As long as I then do x to the 2n plus 1 and divide by 2n plus 1 factorial. Now it'll work. So let's go ahead and do 0 would be positive x to the 1st over 1 is x. There we go. So this goes up nicely. my fault. Increment my counter by 1. When I plug in 1, I get a negative 2 plus 1 cubed over 3 factorial. So this works. Okay. So how, right, does this help? Well, guys, aren't we trying to generate the Maclaurin series not for sine of x, but for sine of x over x? Check this. Our operations for polynomials hold true, so we can simply divide both sides by x. And in doing so, I could divide each term in the sum or difference by x. What? That means my representation for sine of x over x would be given by, well, 1 minus x squared over 3 factorial plus x to the 4th over 5 factorial minus x to the 6th over 7 factorial. Can we generalize it? I bet we can. What's that x on bottom going to do to my generalized term? Well, I'll just take away one of these x's, won't it? So this would now be x to the what? That's it. So I still have my alternating sign, yes. It's still going to be negative 1 to the n, but this becomes x to the 2n. My factorial remains unchanged. That's still 2n plus 1. Quantity factorial. And now I still need to write the Maclaurin series. So what I'm going to do is I'm going to go back to my summation notation, because the series is an infinite sum. It looks like 0 will work out just fine, and negative 1 to the nth over 2n plus 1 factorial and x to the 2n. Let's do a quick check. When I plug in 0, 1, 2, when I plug in 2, I get positive. I get x to the 4th, and I get 2 times 2 is 4 plus 1 is 5 factorial, so it works. Yay, that's it. So was that easier than taking the first derivative, the second derivative, the third derivative, the fourth derivative, evaluating, and then expanding? Yes. All right, let's go ahead and try another one. What? Let's use known. Can't abide by that. Let's use known Maclaurin series to construct the Maclaurin series for the new function. What? Maclaurin series would possibly help us construct the new one for this. F of x equals e to the x squared over 2. So what one do we know? Yeah, we know e to the x. And so while we don't have a Maclaurin series for e to the x squared over 2, we can start with known Maclaurin series, namely e to the x, one of our most famous ones. And what's that given by? Well, we just copied on our table then. What does that look like? Riley?
X to the n.
Oh, we're going right to it. Hang on, let's do some church. So x to the n over n factorial. But did we start at 0? So then we get 0 is 1. So then we get 1, yes? Plus. And then, isn't it x plus x squared over 2 factorial plus? That's pretty sweet. All right, thank you. What are we trying to make though? Oh, we're trying to make e to the x squared over 2. Right? And right now we have e to the x. And so this relies on our substitution that we did, right, 2 class periods ago, when we had to try to make it look like a over 1 minus something, right? And our generalized form started with a over 1 minus x. Now we're shifting gears and looking at a Maclaurin series where I have e to the x. I need to replace that x, right, in my function representation with what I want it to be, the exponent x squared over 2. In doing so, I must then go to my expansion and replace every single x with what I want it to be, x squared over 2, and see if I can simplify. So this becomes a little bit messy at the first step, but it'll work out. this becomes e to the, you guys see that? So this is still 1, but this becomes okay, let's jump inside here. So that original x in my x squared over 2 factorial from e to the x becomes x squared over 2, right? And that's still all squared. This original x from my x cubed over 3 factorial right here becomes x squared over 2. Still quantity cubed all over 3 factorial. You guys see that? This original x from my generalized nth term becomes x squared over 2, all to the nth, and then over n factorial. Our job then is to rewrite this, right, in pretty print as a generalized term so we can have the Maclaurin series and have it match how that goes up. Oh, so I guess we'll do one. We'll do one rewrite so I don't feel bad like I'm sending you off to school without any lunch money. Gosh. Equals 1 plus x squared over 2 plus, what's this going to be? Well, this would be x to the 4th over 2 squared times 2 factorial. This would be x to the 6th over 2 cubed times 3 factorial. This would be, oh, jeepers. This would be x to the, what? 2n over 2 to the n times n factorial. Yeah! That's pretty sweet. So my Maclaurin series then, we have our generalized nth term, is given by n equals 0 to infinity of alternating sign. Nope, no worries. So I can just go right to that, can I? X to the 2n over 2 to the n times n factorial. We'll do a quick check. I'll grab 0, 1, 2, I'll grab 2. When I plug in 2, it should be x to the 4th over 2 squared times 2 factorial it is. We win, math works. That's pretty sweet. Awesome. Okay. So this closure, right, is kind of a double. We're sort of based on yesterday, last class rather as well. The general form for the nth order Taylor polynomial approximation of a function is, go ahead and write that out. Why does a Taylor polynomial mimic the behavior of other non-polynomial functions so well? In fact, transcendental functions like sine of x, e to the x, cosine of x. What is it about that Taylor polynomial that makes it do such a good job mimicking the behavior? And lastly, the general form for the Taylor series representation of a function is. Please have a written response for each of these and be ready to share. I'm going to go ahead and pause the recording to give you a chance to write those down, and then I'll resume the recording for our sharing. Okay, ladies and gentlemen, and so I apologize. Number one, I didn't specify where we're centering it around. So if you did it centered at x equals a, the generalized form will work for everything. If you did it centered at x equals 0, that's fine as well. If we'd like to use a counter, right, other than n, we certainly could do. If this is the nth order Taylor polynomial, we could call it p sub n of x, right? P sub n of x would be given by, and many of you started with your expansion, right? The nth derivative evaluated at x equals a, then times quantity x minus a to the nth, all over n factorial. We could certainly do it with our dummy counter here, call it k equals 0 to the nth term for our nth order polynomial. And then we're evaluating the kth derivative at x equals, well, we could do it at x equals a all over a factorial times quantity x minus a to the kth, and we do that all the way until we got to the nth order. So this is exactly the same form, just with k's instead of n's. You can certainly write it either way. We need to know that we take the nth derivative evaluated at x equals a divided by n factorial, right, for my coefficient, and then times that power term to the nth power. All right, why does the Taylor polynomial mimic the behavior of other non-polynomial functions so well, including sine, cosine, e to the x, all our transcendentals? What is it about a Taylor polynomial that makes it match behavior so well? Did you guys come up with anything to share? No? Let's think about how we constructed our Taylor polynomial. What was our first step for constructing the Taylor polynomial for Bellwork? What did you do first? Riley? Yeah. You evaluate the function at x equals a. Then, not only take the derivative, but evaluated the first derivative at x equals a. What does the first derivative tell you about your original function? How quickly it's increasing. Then you evaluated its second derivative at x equals a. What does the second derivative tell you about the original function? Its curvature and shape. Then you evaluated its third derivative at x equals a. And what does the third derivative tell you? Well, it tells you how quickly the curvature is changing, yes? So it would tell you basically how curved your bowl shape is, right? Then what did you do? Well, in our Bellwork, we stopped at 4, but we still took another derivative, the fourth derivative and evaluated. And that tells us how quickly the curvature, right, is changing, how quickly the rate of change in the curvature is changing. In other words, we're using the exact behavior of my original function to create its polynomial representation. A derivative tells us about the behavior of the original, and a Taylor polynomial is based on the value of the function's derivatives. At x equals a, basically we're telling the function what to be, right? We're using the exact behavior of the original in order to construct the polynomial, and that's why a Taylor polynomial mimics a transcendental function so well. We're using the original function's value and all of its derivatives value to construct the polynomial. So we're using the original's behavior to make a polynomial to represent the original. That's why it works so darn well. And lastly, the general form for Taylor series representation of a function is, now we can go ahead and use our summation notation, and we'll go back to n's. So for us, we're going from n equals 0 to infinity of the nth order derivative evaluated at x equals a all over n factorial times quantity x minus a to the n. Expand it out forever, and we've got the Taylor series. Awesome. What questions do you guys have about our introduction to Taylor series? And your homework is a mixture of generating Taylor polynomials and creating new functions from old known Maclaurin series, like we did with our sine of x over x and our e to the x squared over 2. And that does rely on some of the substitutions you've done before and the expansions, but you can use your table. Awesome. What questions do you have about our discussion today? Great. Then I'll go ahead and save the recording.